Welcome back to this lecture series on pulse width modulation for power electronic converters. So, this is we have been looking at this, we have been going through different aspects of this particular course, pulse width modulation for power electronic converters, and now we have been looking at space vector based pulse width modulation for 3-phase voltage source converters now. So, the present module has actually been focusing on space vector based pulse width modulation, and we earlier covered the concept of space vector, what exactly you mean by a space vector, and we did space vector transformation, how can you transform 3-phase voltages or currents into space vector domain. Then we have been dealing with space vector based pulse width modulation, and we particularly dealt with conventional space vector pulse width modulation, which is a very popular method, quite similar to sine triangle PWM. And then we have also been looking at several bus clamping PWM methods, which are equivalent to the discontinuous modulation schemes that we discussed before in the triangle comparison module. So, we also looked at space vector based bus clamping PWM, and we have also been seeing the equivalence of triangle comparison and space vector approaches to pulse width modulation. So, today we will do a bit of these two again. We would have a review and we would take a look at bus clamping PWM at maybe at a slightly greater depth than we did in the last lecture, and we will also try and see how exactly the similarities between these two methods of triangle comparison and space vector approach, and we will go beyond the similarities. As I have been telling you, space vector approach is actually a little more general than triangle comparison approach. Certain things which are possible with space vector are not possible with triangle comparison. Almost everything that the triangle comparison can do, space vector approach can also do. So, whatever PWM waveforms can be produced using the space triangle comparison approach can also be produced using the space vector approach, whereas the converse is probably not true. I mean, there are certain pulse width modulation methods which are based on the space vector idea. They are not possible using the triangle comparison method. So, some such methods are these advanced bus clamping PWM, and that is what we would be emphasizing on today, right. So, let us just get started with the present lecture, which is primarily on space vector based advanced bus clamping PWM. And if you know advanced bus clamping PWM, you should really know what is bus clamping PWM, which we discussed in the last class. So, we will get into more details of bus clamping PWM before eventually covering this, what we mean by this advanced aspect of bus clamping PWM. To put it in a nutshell, what we are going to look at by means of bus clamping PWM is, you have the situation where one of the phases is clamped to one of the DC buses over some period of time. So, for example, every phase would be clamped to the positive DC bus for 60 degrees and negative DC bus for 60 degrees, and that is why we would call it as bus clamping. What is getting clamped? A phase is getting clamped to a DC bus. So, for 60 degree during the positive half cycle and 60 degree during the negative half cycle typically, and that you would call as a bus clamping PWM method. In advanced bus clamping PWM method, a similar bus clamping will occur. In addition to that, some phases will switch at twice the nominal frequency. You will have a situation where a phase switches at the switching frequency, at twice the nominal frequency, and also at the switching frequency. So, that is why we have this term advanced bus clamping PWM. And now, here we go back to the space vector transformation of 3-phase voltages. We will quickly look at what is this transformation. We have known this, we have been doing this over the last 3 classes. So, V alpha is equal to 3 by 2 times Vrn, and V beta is root 3 by 2 times Vyn minus Vbn. This is for space vector transformation, right, and the same thing has been written in the matrix form here. So, now you have a voltage source converter, and voltage in every leg is a single pole double throw switch. R, Y and B are the midpoints of the legs, and the 3 load terminals are connected here. And you have depending on whether the top is on or the bottom is on, VRO is plus 0.5 VDC or minus 0.5 VDC. Similarly, with Y phase and B phase, and you have 8 different inverter states that are available, and the 2 states here produce 0, they are at 0 states when all the top are on and all the bottom are on, it is 0 state. All the other states are called active states, right. So, regarding the load, we have the load R, Y and B connected like this, and the neutral point N is not electrically connected anywhere else except through the windings to these terminals. So, we are looking at a 3-wire connection, that is how the load is now. And in this kind of a scenario, what we are doing is, so we have, these are the vectors. So, there are 8 inverter states as I mentioned to you, and when the inverter is in the state plus minus minus, for example, what we mean by that is the R phase top device is on, Y phase bottom is on and the B phase bottom is on. Under such condition, what happens is the inverter applies, this is the voltage vector now. that is there is some VRO is plus VDC by 2, VYO is minus VDC by 2 and VBO is minus VDC by 2, and this produces certain sets of 3 phase voltages VRN, VYN, VBN applied on the load, and that in turn produces a voltage vector shown like this, and the 6 active states produce 6 active vectors which are shown like this, all are of magnitude VDC and they are separated by an angle 60 degrees as shown here. And what we do here in space vector based PWM is there is a revolving reference vector. Instead of 3 phase sinusoidal wave, you use a voltage vector and the voltage vector is revolving. It revolves at the modulation frequency, it has a constant magnitude under steady state. We sample it every time and this is how the samples will look over a cycle, right. Then you consider a particular sample, there is a particular sampling interval or a subcycle duration time Ts, and within the Ts let us say if this is what is your reference vector commanded, and this reference vector falls between vector 1 and vector 2. So, between vector 1 and vector 2. So, the active vectors V1 and V2 are used, and in addition to this null vector 0 to produce this particular vector of magnitude Vref and angle alpha. So, you do this by applying the active vector 1 for T1 duration within Ts and the active vector V2 for T2 duration within Ts and the null vector for the remaining duration Tz, and you get a resultant vector which is equal to the commanded reference vector. So, that is the equations here. This is the commanded reference vector and this is the applied vector here, and the active vector 1 is to be applied for duration T1 and active vector 2 for T2 and null vector for Tz. How do you calculate T1, T2 and Tz? You get them here. This is T1 in terms of Vref and alpha, T2 in terms of Vref and alpha, and Tz is Ts minus T1 minus T2. We've seen this in the last 2-3 lectures, just having a quick brush through of all that now. And in the conventional switching sequence or in conventional space vector PWM, what we do is you apply the null vector. You start with the null vector, go to active vector 1, 2 and come back to the null vector. So, when you do this, the null vector is in the first instance, the null vector is applied using the 0 state minus minus minus. At the last instance, the null vector is applied using the 0 state plus plus plus. So, you for example, you start with minus minus minus, all the bottom device on, switch R phase, then you go to the active vector and you apply this for duration T1 and then you switch your Y phase and you go to active vector 2 and you stay here for duration T2 and then you switch B and you go here and stay for duration B now. So, you can go back to the previous lectures in case you have any further this thing on that. So, this is what we have been looking at, and in the next subcycle you will come back. So, you start from a 0 state, go to active state, one active state, another active state and then to the other 0 state and you come back. This is the conventional switching sequence now. So, this is what is shown with against time. This is the inverter state applied against time. You have inverter state 0 minus minus minus, you have inverter state plus minus minus, you have inverter state plus plus minus and plus plus plus. These are applied for durations T0, T1, T2 and T7 respectively as shown here now, right. So, in the next subcycle they are applied in the reverse sequences 7, 2, 1 and 0, plus 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 is applied first, plus plus minus next and plus minus minus and then minus minus minus. So, the states are applied in the reverse sequence, right. So, these are the pole voltages as we saw, and we also saw the equivalents now. So, the pole voltages are like this, and if that is the pole voltage, the dashed line indicates the average pole voltage and the scaled version of the average pole voltage is MR star. Similarly, the scaled version of the average pole voltage is VYO average and VBO average would be MY star and MB star. Now, if you have MR star, MY star and MB star, you can compare them with triangular carrier as shown here, and the intersection of these MR star, MY star, MB star with the triangular carrier would give you the switching instance of the respective phases. So, you can also produce the same PWM output from this so called triangle comparison approach, and that is what we emphasized in terms of equivalent now. So, what needs to be done? You have to produce the appropriate value of MR star, MY star and MB star. That is how we saw that. Now, this is your MR. If this is your MR, what you do is you need to know what is your common mode component, and the common mode component we found was 50% of the middle value. For example, you take this region, let us say 0 to 30 degree, B phase is the highest, which you could call as M max, Y phase, this is B phase sign here, and the R phase sign is the middle valued sign, you can call it M mid, and the B phase or the yellow phase which I have given in green color is the minimum most negative one, and we can call this M minimum. So, you take M mid is this red phase, take 50% of that, is what is shown by the blue one. And similarly, between 30 and 90 degrees, red phase is M max and this M is, that is the blue phase is lower than the red and it is higher than the yellow phase. So, this is what gives you your M mid, this line. So, half of that is what is given by here. So, this is half of M mid, that is your common mode signal. You add that common mode signal, then your R phase sine wave, which is like this, becomes a modified waveform as shown like this. So, that is your R phase modulating, modified modulating, that is your MR star. Similarly, here is your MY star, here is your MB star. You compare these with triangular carrier to produce space vector PWM. This is a very, very efficient way of doing it. So, this is what we looked at, and this shows that they are equivalent now. So, this is only to show that you can go a little higher than that, that the modulation, this is 1 corresponds to the peak of the carrier. You see that the peak of the sine wave is 1.15, some 15% higher than the peak of the carrier. Still, what happens when you add the common mode component, the effective value comes below and the peak value is just touching 1. So, the peak value of MR star not exceeding 1, you can go and have a peak of up to 1.15 for MR. So, you are able to pack some 15% higher fundamental voltage here, just as we did in third harmonic injection with 1/6 third harmonic injection. So, you do this now. So, this is a look at conventional space vector PWM from the space vector point of view, from the triangle comparison point of view. So, then the bus clamping, what we did was, see, this is a null vector, the total null vector has to be applied for Tz seconds. In conventional PWM, you apply this for Tz by 2, you apply that for Tz by 2. Somebody can ask a question, why not apply only 1 0 state? Why not apply minus 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 alone for the entire Tz? So, you can still produce the same average voltage vector. You apply this for Tz seconds, then move here and stay here and apply for T1 seconds, and then after that you switch Y phase and go here and apply this for T2 seconds, and the result is the same. This is the same average vector as what you would get, if you applied this for Tz by 2 and if you applied that for Tz by 2. So, now what you do is you are saving one switching, that is what you do. This has the effect of increasing the harmonic distortion that we will see a little later, and but at the same average switching frequency you can also reduce the harmonic distortion using this, but those are discussions we will take up in the module on analysis of current ripple. So, right now we will just look at the pulse width modulation generation of PWM waveforms. You see that there is one switching less, you go 0, 1, 2, and in the next subcycle you can come 2, 1, 0. So, what happens because of this is the B phase, you see it is always negative here, the B phase is getting clamped to the negative DC bus. The same way you can skip the 0 state minus 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 totally and apply only plus 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 for the entire duration Tz. So, from plus 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 you switch B phase, you go to plus plus minus, and you switch Y phase and you go to plus minus minus, and the same way you can go back 1 2 7 7 2 1 1 2 7 7 2 1 and so on. Excuse me. So, in this case what happens is R phase is always connected to the positive. Here you see R is positive, here also you see R is positive, here also you see R is positive. So, R is always connected to the positive bus. So, this is R being positive. Alright. Now, let us move to the other one. So, that is this is 1 to 7 or 7 to 1 seen in the time versus time now. So, this is 1 and 2, this is plus minus minus, plus plus minus and plus 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 applied, and here you have the reverse sequence, and R is clamped, as you can see VRO is always equal to plus VDC by 2, and you take VYO, it switches as we have shown here, and VBO it switches like this now. And once again you look at it here, there is VRO average is equal to VDC by 2 here, and VYO average is shown by the dashed line, and VBO average is shown by this dashed line. MR star, MY star and MB star correspond to the average voltages VRO average, VYO average and VBO average, right. So, you have this average, you have MR star, MY star and MB star, you can compare them with triangular carriers. Now, what you are doing, you can once again you will be able to generate the appropriate switching instance. So, to say that you can do the calculations either in the space vector domain, or you can go and produce these waveforms from the triangle based on the triangle comparison approach. So, all that you are doing is you are effectively adding a common mode. What you are dividing the null vector time. You had a 0 here, you are entirely applying Tz. It just has the effect of adding a common mode here. There is nothing more than that. So, we move here. This is the same 0 1 2 and 2 1 0 here. This is a case where the common mode is negative. You can see that the same MR, MY, MB results in MR star, MY star and MB star here, such that MB star is equal to minus 1 or it is equal to the negative peak of the carrier. MB star is equal to the negative peak of carrier. All the values have decreased from MR, MO, MB, some negative common mode component has been added here to come up here. Whereas in the earlier case, the common mode component added is positive, so that MR, which is the highest of the 3, is gone and is become equal to plus VDC by 2, or which is equivalent to the V peak of the carrier. So, here you have added a positive common mode component such that your M max becomes equal to the V peak. Here you have added a negative common mode such that your M minimum is equal to minus V peak. That is how you do now. As a result of this addition of common mode components, you end up applying only one 0 state fully and or the other 0 state fully now, and this has the effect of clamping one of this now, and this is 60-degree clamp which we saw earlier. Now, we have to take a slightly careful look at this, because this is very important for the advanced bus clamping which we need to be doing now. So, as I said here, when you use the 0 state 7 to 1, let us look at that. So, 7 has R phase is positive, 2 and 1, in all these cases you find that R phase is positive. This is what we had seen earlier. So, what happens is, in this region you have R clamped to the positive DC bus now. So, in sector 1 you can either skip minus or plus. By skipping minus we have got R clamped to the positive bus. You take the 0 1 2 now. If you take 0 1 2, what happens in 0 1 as well as 2, you will find that this is 0, this is 1 and this is 2. So, I have encircled all these 3. In all these 3 you find that the B phase is clamped to the negative bus, and therefore, this leads to the clamping of B phase to the negative bus. So, in sector 1 you have two options, either to use the 0 state 0 throughout or the 0 state 7 throughout. Either use the 0 state 0 throughout or 0 state 7 throughout if you want to indulge in bus clamping. In either case, Y phase has to switch. Why? Because you have active vector 1 and active vector 2. If you want to make a transition from active vector 1 to 2 or from 2 to 1, you have to switch Y phase, and both these active states have to be applied. You see it is plus minus and you see it is plus minus, and therefore, Y phase always has to switch and it cannot be clamped. What can be clamped? Either R phase or B phase can be clamped. If the null state that you use is plus and you avoid this other 0 state minus, then you have the result of R phase getting clamped to the positive bus. Again, if you have a reference vector falling within sector 1, and if you are using minus and not using plus, you will have this of B getting clamped to the negative DC bus. So, you can actually call in this sector, there is some terminology, the Y phase can be called as the unclampable phase. Y phase cannot be clamped here. Why? Because for switching between the two active states, you need to switch Y phase, and you have to apply both the active states to produce an arbitrary reference vector. To produce any arbitrary reference vector, let me just draw one vector here. If you need to produce any arbitrary vector as shown here, you need to apply, you need to apply active vector 1, active vector 2 on the null vector. When you have to apply both the active vectors, you certainly have to switch Y phase, and you cannot avoid switching that. And you can call Y phase as the unclampable phase in this sector, it cannot be clamped. Whereas R and B phases can be called as the clampable phases in this sector, and R is particularly positive clampable phase. You can clamp it only to the positive phase, you can't clamp it to the negative phase, and B can be called as the negative clampable phase. These things you can very clearly see only from these 4 inverter states, and by avoiding 1 0 state you can see what is the effect on that. You can also look at it from different perspectives. Now, you look at it now, let us try and correlate this reference vector. Let us say this is the reference vector now. There is some position it corresponds to. This position, what does it correspond to in terms of the fundamental angle? If the reference vector is here, the reference vector has been rotating in the anti-clockwise direction. So, what has happened is, this vector 1 corresponds to the positive peak of R phase. So, this reference vector, this position indicates a time a little after R phase positive peak. So, this is a region in the fundamental cycle where your R phase is close to the positive peak. How about the other phases? Now, you look at, this is your R phase axis. Where is your Y phase axis? This is your Y phase axis. You can call this as positive Y phase axis, and you can call this as negative Y phase axis, and therefore, this line this line is the 0 crossing of y phase. This line corresponds to 0 crossing of y phase. So, you can see that r phase is close to its positive peak and you can see that y phase is close to 0. What else? B phase, and this is r phase axis, this is y phase axis, and this is B phase axis, and this is positive B phase axis and this is negative B phase axis. So, this you can say you are in a region where the B phase is most negative, is close to its negative peak. So, that is what you get in this region. If you are in sector 1, you can the reference vector is between active vector 1 and active vector 2, and if you look at it in terms of 3 phase sinusoidal waves, what you would see is you would see that your R phase voltage is close to its positive peak and B phase voltage is close to its negative peak and the Y phase is close to its positive 0 crossing. I am saying that this is positive 0 crossing. Why? You can also see that this part is the positive half cycle and this part is the negative half cycle. You see it is plus minus minus here and from here it is plus plus here. Let me just choose some other color ink and point out that to you. Now, let take Y phase. I am circling it with this green ink now. You see that it is plus 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 here and you can see that it is all minus 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 here. So, this part, this half cycle corresponds to negative half cycle of Y phase and this half cycle corresponds to the positive half cycle of Y phase. Okay. So, we need to be increasingly clear about the correlation between 3 phase sine waves and the position on the reference vector. We need to be able to correlate these two very well now. So, we call this as bus clamping PWM because every phase gets clamped to one bus. Now, if you take here, this is also R is connected to the positive DC bus here also, and the same way as we looked at yesterday, if you here also here you will find R phase is once again clamped. R phase is clamped to the negative bus. Here also you will find R phase is clamped to the negative bus. How is that? Excuse me. So, 0, 3, 4 or 0, 5, 4. When you use 0, it is minus minus minus. You go to 3, it is minus plus minus, and 4 is minus plus plus. So, you see that R is negative, then both the active states are applied, and the 0 state applied is 0. Similarly, 0, 5, 4, in 5 as well as 4, R phase is negative and this is 0, it's minus minus minus. So, this is what you have. So, what else you have? This is R minus and R minus, this is R plus and R plus. So, this corresponds to the middle 60 degree duration of the positive half cycle of R phase. Now, this line corresponds to the positive 0 crossing of R phase. This is the positive peak of R phase, this is the negative peak of R phase, this is the positive 0 crossing of R and this is the positive peak of R phase, which we can call as 90 degrees now, right, and this line corresponds to 60 degrees and this one corresponds to 120 degree. Between 60 and 120 degrees you have R phase clamped, that is R phase is clamped during the middle 60 degree duration of its positive half cycle, where it is clamped to the positive DC rail, and you take the other corresponding 60 degree duration in the negative half cycle. This is the middle 60 degree duration in the negative half cycle and you see that R phase is clamped to the negative bus and you see it is R minus and R minus here. Is that fine? So, the same way you will see that everywhere every phase will be clamped around its peak value. Excuse me, let us just do it for one more phase so that it becomes clearer, right. So, you have R and R. You take it, if you look at Y, let us say you look at 7, 2, 3. What is 7, 2, 3? Plus 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 and 2 is plus plus minus and 3 is minus plus minus. So, Y is connected to the positive, is clamped to positive phase here, and 7, 4, 3, 7 is plus 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 and 4 is minus plus plus and 3 is also minus plus minus. Therefore, here also Y is connected clamped to the positive bus here. The same way you will find that Y is clamped to negative bus in these two regions and you will have B clamped to negative bus and here you will have B clamped to positive bus. You will find that everywhere it is in the middle 60 degree duration of its positive half cycle. If you take Y phase, this is the 0 crossing of Y phase and this is the positive peak of Y phase and this is the middle 60 degree duration in the positive half cycle of Y phase, it is clamped here, and that is the reason there is this thing called 60 degree clamp PWM. It is just a name after all, sometimes it is called DPWM 1 in some literature. we call it 60 degree clamp because it is clamped, whenever a phase is clamped during the middle 60 degree duration is half cycle, in every half cycle we could call it as 60 degree clamp PWM. And this is the modulating, these are the modulating signals as we saw before. Now what if you compare this with the triangular carrier, you can observe that the phase is clamped here, so it does not switch at all here, whereas a phase would switch here, for example at the carrier frequency, it will switch at the carrier frequency. So what will happen is, here it switches at the carrier frequency, here it switches at the carrier frequency, whereas here it is clamped. So you can define as what is called as average switching frequency. So the switching frequency here is Fc, here is Fc, here it is 0. So the average switching frequency will be 2/3 of Fc, that would be the average switching frequency over a line cycle. So you are able to save about 1/3 of this cycle. That's what that's one advantage of bus clamping PWM. You are able to reduce the number of switching cycles, and if you are able to reduce the number of switching cycles, you are also able to reduce the number of switching losses now. So I am doing this because we just have to get into the advanced bus clamping now. So this is again, you have your 30 degree bus clamping, and in this 30 degree bus clamping, if you just let's focus just on the R phase alone, you will see that R phase is clamped to the positive bus here and R phase is clamped to the negative bus here. Again you will find that R phase is clamped to the positive here, negative, and here also R phase would be clamped to the negative bus here. And if you call this is what is 30 degrees, this would correspond to 60 degrees. If you start your cycle at 0 degree, this is 0, there is R phase 0 crossing, 30, 60, this is 90, this is 120, this is 150, this is 180. And you can see that R phase is clamped between 120 and 150, and it is also clamped between 30 and 60. You see 0 to 90 is 1/4 and 30 to 60 is the middle 30 degree duration in a particular quarter. Here again you see it is in the middle 30 degree duration in another quarter. Here also you will find that it is clamped to the middle 30 degree duration in these quarters, and hence we call this as 30 degree clamp PWM. So in this, what you will find is not only R phase, you take any phase Y or B also. Every phase you would find that is clamped to its DC bus during the middle 30 degree duration in every quarter cycle, right, and it is clamped to the positive bus if it is positive half cycle, it is to the negative bus if it is a negative half cycle, and this is what is the corresponding modulating signal that we had seen here. So here again the switching frequency is 0, here again the switching frequency is 0, here it would switch at carrier frequency. So once again what you will have is for 60 degrees it is not switching, 30 degree here and 30 degree here, and your average switching frequency will be 2/3 times Fc, where Fc is your carrier frequency, right. So we would go to advanced bus clamping PWM, where you will not just have these two cases, that is switching at carrier frequency and switching at 0. You will also have a situation where they switch at double the carrier frequency. So this is again continual clamp, which we do this. Continual clamp is a generalization of 60 degree clamp. So you have 7 to 1, you have 0 1 2. In the case of 60 degree clamp, what we found was the changeover of 0 state occurred at the middle of the sector, that is what is gamma is equal to 30 degree. Now it does not have to be at gamma is equal to 30, it can be at any arbitrary gamma. Gamma can vary anywhere between 0 and 60 degree, and that is what you would call as continual clamp. Why do we call this continual clamp? As I mentioned the other day, so here you find that R phase is clamped here, you find R phase is clamped continuously to the positive DC bus, because active state 7 is used. All these states 1, 2 and 6, if you see here R is positive, here also R is positive, here also it is positive. So in all these active states R is positive, and you are using only plus plus plus, and you are not using minus minus minus. Because of that, R phase is getting clamped to the positive bus when minus 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 is not used, and you see that R phase is clamped over this thing now. This is a 60 degree duration now. So it is continuously clamped for a 60 degree duration, and therefore you call this continual clamp PWM. So this is not exactly between 60 to 120 degree. So this can be anywhere, this can be anywhere. This can actually start from 30 to 90 degrees, and this could be anywhere between 90 to 150 degrees. So that is what is shown here in this waveform. You can see that it is clamped, it shows for some particular value of gamma. If the value of gamma is equal to 60 degree, it will come to 90 to 150 degree, and otherwise it is if gamma is 0, it could be 30 to 90. If gamma is equal to 30, it will be exactly 60 to 120, as in the case of 60 degree clamp now. So we go to split clamp, which is again a generalization of what we saw before, that is 30 degree clamp. So this is, you have R phase clamp to the positive bus, here also you have R phase clamp to the positive bus. So this is 30 degrees. sorry, this is 30 degrees, and now this is 30 plus gamma, this is 150 degree, sorry, this is 90 plus gamma. So, here it is gamma. So, what you have is this duration is gamma and this duration is 60 minus gamma. So, it is clamped for duration gamma in one quarter cycle, and it is clamped for a duration 60 minus gamma in the next quarter cycle. So, it is split clamp. A particular cases when gamma is equal to 30, and that is what is called as your 30 degree clamp. So, this split clamp PWM hasn't been realized, I mean hasn't been investigated much in the literature, but I would say that this split clamp PWM has better harmonic distortion than this continual clamp PWM. I am just making an assertion here. We'll prove this when we look at this thing, look at the analysis of line current ripple. So, right now let us just take it that it's going to be better than that. All right, then so this is how the split clamp PWM signals are going to look like. Now, let us just take a look at that. We have been looking at going through both triangle comparison and space vector approaches. We looked at conventional space vector PWM, we are looking at bus clamping PWM, but in all these cases what we have been looking at is, we are not only looking at it from the space vector point of view, we have been looking at it from the triangle comparison point of view also. Now, let us just make a few points here before we proceed to the advanced bus clamping ones here. You see that both the 0 states are employed in each subcycle by continuous PWM method. Now, conventional space vector PWM is a continuous PWM method. Now, this is a continuous PWM method. Why would you call it as a continuous PWM? You see that the modulation signal is a continuous function of time. Not only this, you can add sine, and to sine you can add any third harmonic. Instead of this, you can also add a third harmonic. You can add anything, any common mode which is a continuous function of time. The sine wave itself is a continuous function of time, and to that if you add a common mode component which is also a continuous function of time, the resulting modulating signals such as this are also continuous times. Now, if it is continuous, so what? Now, let us take it is continuous and it is in linear modulation. You take this. Now, let us say this angle is 60 degrees, though you can't read that very clearly. You can see that this is 60 degrees. Let us consider a carrier cycle at 60 degree. Now, what happens now? You look at what is your R phase. This is your R phase modulating signal. This is MR star. And what is your Y phase modulating signal? This is MY star. And what is your B phase modulating signal? This is MB star. So, you see that you have, where is your carrier peak? The carrier peak is here. Do you want me to draw? Let me just draw that. So, the carrier peak is here. The carrier peak is here. This is the positive carrier peak. This is the negative carrier peak, right? Let me choose red ink and show where you have the red one. Yeah. So, if you look at the red phase is here, or maybe I will just choose a black color or so that everywhere you can get. So, this is your red, this is your yellow phase, this is your blue phase. Just to avoid confusions, I will make this further clearer. This is plus Vp, this is minus Vp. And what is this? This is MR star, this is MR star. And what is this? This is MB star, and this is MY star. So, you see that between Vp and MR star there is some gap. So, there is during this interval is when 1 0 state is applied. So, during all during this small interval, what you will find is the carrier will be greater than MR star, MB star as well as MY star. The carrier is going all the way from Vp to minus Vp. If you draw the carrier on this, it will almost look like a straight line. There is a small slope, it will almost look like a straight line. So, I am not drawing the carrier really speaking. So, it is going to be like this. So, initially all the phases are going, if you consider a carrier dropping from plus Vp to minus Vp, initially you will find all the three signals, the carrier is greater than all the three signals MR star, MY star and MB star. Therefore, you will have 0 state applied now. Here you will find R phase alone switches, and so between these two you will have R is positive, plus minus minus is what you will get here. And this MB star, after this B phase will also switch, you will get plus minus plus in this interval, and after that you will get plus plus plus. So, what you see is one active state here, another active state here. When you start, it is 1 0 state which is minus minus minus. When you end, it is another 0 state plus plus plus. So, this is because there is any continuous modulating signal. Now, on the other hand, if you do not have a continuous modulating signal, you go to a discontinuous modulating signal like this and you consider a particular instant as shown here. Let us say consider the instant 100 degrees, you consider this instant 100 degrees, and here this is equal to your Vp, this is also equal to your MR star. So, even as you start, your R phase is always positive, R phase is never negative. Here if you look at this, so this is MR star, and where is your My star and MB star? If you look at here, we will take this. So, this is My star and this is MB star and this is minus V peak. So, what you get here is you get your Vp and MR star are equal. So, 1 0 state is never applied. So, R phase is always positive and towards the end there is a 0 state applied. In this case, when you are between that, when your carrier is falling and the carrier is below MB star, you will get the carrier is lower than all the 3 values MR star, My star and MB star. Therefore, all the positive devices will be on, you will have plus plus plus, but minus 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 is never applied. So, whenever you do not have discontinuity, whenever you have the 3 signals MR star, My star and MB star within minus Vp and plus Vp, not touching, not equal to that. So, like the M max, whatever is the maximum modulating signal is lower than plus Vp and the minimum modulating signal is greater than minus Vp, you will have this thing. So, whenever you have this continuous modulation, whenever you have a continuous PWM and it does not exceed. So, the 3 modulating signals are there M max, M mid and M min, none of them exceed plus Vp or minus Vp. M max is lower than plus Vp and M min is greater than minus Vp. Under that condition, you will see that both the 0 states are applied now. This happens in conventional space vector PWM. Only thing both the 0 states are applied for equal durations. This happens in sine triangle PWM, but both the 0 states are not necessarily equal. And you had third harmonic, both the 0 states are applied. You consider third harmonic injection with k equals 1 by 4, then you get a situation where both the 0 states are applied more or less for equal durations of time. Okay. So, on the other hand, if you look at the bus clamping PWM method, the discontinuous PWM method, you will find that there is only one 0 state used in a subcycle. So, what you really see here is it is division of null vector time between the 2 0 states. This is what changes, division of null vector time between 2 0 states now. How long you are applying 0, how long you are applying, and that is equivalent to whatever common mode is being injected. So, we have some common mode that is being injected. So, in all the cases, now there is certain common mode has been injected here, that is a positive common mode now. On this itself, let me just draw and give some indication. Let us say that common mode is different. Let me say the common mode is different. So, all of them are a little lower than that. This signal is a little lower, and again this average voltage is also little lower, and this average voltage is also little lower. All the 3 average voltages or all the 3 MR star, My star and MB star, I have added some delta M, negative delta M through all of them. So, they have all reduced. Because of this, what happens? If you finally look at it, this is your 0 vector time. This has come down. What was originally your 0 vector time? This is T7, entirely T7. Now, this is what is your T7. This is what is your T7. And T1 and T2 are unchanged. T1 and T2 are unchanged. Why? Because if you look at this, this has come down and therefore, the switching instant has shifted. So, now this switching instant is also shifted. Therefore, effectively the duration for which T1 is applied is unchanged. Excuse me. For T1 is applied is unchanged, and again the duration for which T2 is applied is unchanged, the duration for which T7 applied is changed now. So, what happens because of that? Anyway, you see that there is T0 here, this is T0 and this is the duration for which T0 gets applied, and T0 plus T7 is equal to this original Tz. So, what happens is when you add a common mode component, simply division between T0 and T7 just changes. Original sine waves MR, My, MB, and from there you have added MR star, My star, MB star, and the particular case we considered was where the positive common mode component was is added, and MR star becomes equal to plus Vp. So, what has happened is entirely only the 0 state 7 gets applied for the entire duration Tz, and minus 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 never gets applied. On the other hand, I have shown for another example, what I have drawn here is some other value of common mode. If it is some other value of common mode, what you see is you get both 0 and 7 are getting applied, but the sum of T0 plus T7 is equal to the old Tz. That is how it happens now. Therefore, you get that is the point that I was making. The null vector time is what is different. The division of null vector time between the two 0 states, that is equivalent to injection of common mode component. When you add common mode component, what exactly happens is the active vector times do not change, but the time for which the two 0 states are applied changes, but the total null vector time is still the same now. This is about triangle comparison and space vector approaches, and we just go down and to see space vector based advanced bus clamping PWM. Here also what you have is one active state is applied twice in a subcycle. That is the important difference. In the previous cases, all the previous cases, you have an active state getting applied only once in a subcycle. You have active state 1 and then active state 2. Here what you can think of as active state 1, 2 and back to active state 1. You have a situation where one phase switches twice while the second phase switches once and the third phase is clamped. In bus clamping, you will have this situation where one phase switches once in a half carrier cycle and the other phase is clamped. I mean two phases will switch like this and one phase is clamped here. In advanced bus clamping, you have one phase switching twice and the second phase switches once while the third phase is clamped. This is a difference now. And now we are going to say space vector approach is more general than the triangle comparison approach, which is what we are going to bring out now. So, this is your clamping sequence. Just start with that clamping sequence where you are applying 0, 1, 2, minus, 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 plus, minus, minus and plus, plus, plus. This is going like this. So, you have VRO switching like this and this is VYO and this is VBO, which is always equal to minus VDC by 2. So, now this is 0, 1, 2, 1 and 1, 2 and 0. Now, if you look at this 0, 1, 2 and whereas here it is 0, 1, 2, 1. What am I doing? I am applying 0 for T0 seconds, then I am applying 1 not for T1 seconds, but for 0.5 T1 seconds. Then I am applying T2, I mean active vector 2 for T2 seconds as before. Then I am going back to state 1 and applying this for 0.5 T1 seconds. So, this is null vector is applied through only one 0 state minus, minus, minus and Tz. So, if you take active vector 2, that is applied for T2 seconds as determined by calculations. We have an expression, T2 is Vref sin alpha by Vdc sin 60 multiplied by Ts, etc. Similarly, you have T1, some required T1. That T1 we are not applying, the active, we are applying active state 1 twice. We are going from 0 to 1, 2 and back to 1, right. So, what happens to you? Now, you see that R phase switches like this, whereas Y phase switches twice. When you are going from 1 to 2 and 2 to 1, Y switches twice like this. This is the difference that I was saying now, which happens in. So, and one of the phase is clamped now because you are using only one 0 state, plus 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 is never used. You see that B phase is always negative and therefore, you call it a clamping sequence because B phase you can see it is clamped here. It is always equal to minus VDC by 2 in this case, whereas Y phase switches twice and therefore, you can call this double switching clamping sequence. In this particular example, your B phase is clamped to the negative bus and Y phase is switching twice, and 0, 1, 2, 1 if is what you use in one subcycle, 1, 2, 1, 0 is what you can use in the next subcycle. So, here again whatever is your T1 dash, you are applying active state 1 for 0.5 T1 dash and then 0.5 T1 dash later, right. The same way, if you start with the clamping sequence 7 to 1, 1 to 7, this is 7 to 1, 1 to 7 and R phase is always clamped positive and Y and B switch once each in every half carrier cycle. Now, you go here, this is double switching sequence 7 to 1 2, this is not 7 to 1, this is 7 to 1 2. You apply 7 for a duration T7 is equal to Tz. Then you apply active vector 2 plus plus minus. You do not apply this for the entire duration T2, you apply it only for 0.5 T2. So, from 0.5 T2 what you do? You go to active vector 1 and apply it for T1 seconds. Then from there what do? You go and apply active vector 2 for 0.5 T2. This is what you do. So, active vector 2 gets applied twice because why? What happens because of this? You see that the phases, you look at it in terms of phase, you see that Y phase switches twice. You see that Y phase switches twice. So, there is and B phase switches just once now. So, you look at it here, B phase switches once, Y phase switches twice, R phase is clamped. Therefore, because R phase is clamped to the positive bus, you can call this as clamping sequence, and Y phase switches twice, you can call it double switching clamping sequence. And what can be clamped? It can either be R phase or B phase in sector 1. Y phase cannot be clamped, and in this case Y phase is double switched now. You can similarly think of other examples. See here I have just shown this in a different on the space vector plane for an easier understanding. So, what do you do here? Let us say you start from 0, minus minus minus, and then you go here, you switch your R phase, that takes you to plus minus minus. So, instead of staying here for t1 seconds, you stay here only for 0.5 t1 seconds. From here you switch which phase? Y phase, and go to 2. So, you are an active vector 2, you apply active vector 2 for t2 seconds, and from here you switch back your Y phase and you return back to active vector 1 and stay here for t1 by 2 seconds. So, tz seconds here, t1 by 2 seconds here, t2 seconds here, and t1 by 2 seconds here. So, you end up getting the same average vector now, because you have applied the null vector for a certain time, and t1 is not applied continuously. Active vector 1 is applied for t1 by 2 seconds now and t1 by 2 seconds later, and you still have this fraction is still t1 upon ts times v1 vector, and vector 2 is applied for t2 seconds. So, this fraction is vector 2 multiplied by t2 upon ts, and what you get is the same reference vector. This is the same reference vector you generate with the conventional sequence, where you apply both the 0 states for equal durations of time, and if you skip one of the 0 states through bus clamping, you can produce the same thing. And now using double switching clamping sequences, you are able to produce this now. Right now, we have moved off. We are now not looking at the inverter as 3 different phases, or 3 independent phases. We are looking at the inverter state, and that is why we are able to say. The question is, we are asking a question: why should I apply this active state continuously for t1 seconds? Why not I apply it later? Why not I apply it for once more? So, that is the answer to that now, because from the space vector domain you know that you have to apply the active vector 1 for t1 seconds and active vector 2 for t2 seconds and the null vector totally for tz seconds. So, it does not matter in what sequence you apply, you have to move in a particular sequence so that you do not switch unnecessarily. You see that every transition you are switching only one phase and you are changing from one state to another. Here only R switches, here only Y switches. For every state transition there is only one phase switches, other than that we are not doing anything. So, now it is totally 3 switchings. We are avoiding B phase switching and we are switching Y phase twice. You may ask what is the advantage. Firstly, I am telling you it is possible to do this now, and we will come to advantages a little later. One of the advantages is that at high modulation indices, these kind of switching sequences can give you a lower harmonic distortion, which we will address in the next module. And it is also advantageous to reduce the switching losses under certain circumstances, and particularly at high power factor this kind of switching sequences are helpful. Again I will talk to you on that later when in the module on switching loss. Right. So, this is about 7212. Here instead of using 0 I am using 7, and from 7 I go to 2, I stay here for t2 by 2 seconds, I switch Y phase and go 1 and apply active vector 1, stay here for t1 seconds and switch back and come here and apply this for the remaining t2 seconds. So, overall I am applying active vector 1 for t1 seconds and active vector 2 for t2 seconds and the null vector for tz seconds. So, I will get the desired average voltage vector. So, that is what we are doing. You can apply the vectors in different sequences, but this null vector is totally applied for tz seconds, this is totally applied for t1 seconds, and this is totally applied for t2 seconds as required, and therefore, this produces the same average vector. So, what we are trying to say repeatedly is the same average vector can be produced by applying the voltage vectors in different sequences. So, there are different sequences are possible is the bottom line that we have been trying to emphasize now. If you can see this is very similar to our 60-degree clamp. This is 60-degree clamp I have just changed. What is the change I have done here? Very easy to see. You see I have set 7212 here instead of 721. Instead of 012 I have set 0121. You see this. I have just changed the switching sequence. Nothing more I have done. That is the reason I was emphasizing on bus clamping PWM so far, because it is very important for us to go to this advanced bus clamping PWM. Sequence 721 and 012 I have replaced by 7212 and 012 is shown here. What happens because of that? Here, because we are not using minus at all, R is clamped to the positive bus. You can see that it is positive, R is positive here with both the active states, and you are using only 0 state 7, where again R is positive, so it is R is positive now. Other than that, what happens between 2 and 1? This is 2 and 1. So, what happens is Y phase switches. Y phase switches R plus, and I am writing it as Y2. The notation here is Y phase switches twice. Here what do I do? Here also I will see that R switches, R is positive, And how about Y phase? You can see that Y phase is, this is 6 and 1. So, here this is 6, this is 1. So, 6 and 1 Y is like this. If you look at the other side, this is R, 6 and 1, and what switches is B. This is B is minus and this is plus minus minus here. Here you see that B is switching twice. So, here you find that B switches twice now. Let us go back to our sector 1. In sector 1, what happens when you use 0 state 0? It is clamped like B negative. This is very similar to the 60 degree clamp before. Now, which phase switches twice? Y phase switches twice. And this is the 0 crossing of Y phase. So, what you can see is R phase is clamped. Where is R phase clamped? R phase is clamped during the middle 60 degree duration. Here also you will find that R phases will be clamped during the middle 60 degree duration to the positive bus. And now what you say Y phase? Now, Y phase double switches here. This is Y phase double switches here. Y phase is double switching around the 0 crossing. This line is the 0 crossing of Y phase. This line is the 0 crossing of Y phase now. So, this is a particular advanced bus clamping PWM, which is an extension of 0 degree clamp PWM. I have replaced the sequences by the advanced bus clamping sequences. What it results in exactly is clamp during the middle 60 degree duration, as I showed before. In addition to that, Y phase or any phase is double switching for a 60 degree duration around the 0 crossing. So, now you have a situation where let us call for 60 degree centered around the 0 crossing, a phase double switches, and 60 degree centered around the peak, it is clamped, and the remaining times a phase switches at the nominal switching frequency. So, the phase overall has an equal average switching frequency. What happens is there is a kind of redistribution of switching frequency that happens. It switches more often around the 0 crossings and it switches less often around the peak values of these voltages in this case now. The average switching frequency is still the same as in the case of conventional space vector PWM. So, this is from advanced bus clamping PWM. I am coming to 60 degree clamp now. The same way I can do this, 30 degree clamp I have converted into advanced bus clamping PWM. You can see the sequence. Instead of 0 1 2, I have written 0 1 2 1. Instead of 7 to 1, I have written 7 to 1 2, and I have made similar changes in all the other sectors. Nothing else I have done now. Now, because of this, what is going to happen? Here it is R is positive and here B is negative as before. In sector 1, R can get clamped to the positive bus if plus 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 alone is used, and B gets clamped to minus negative bus if minus 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 alone is used, and that is what happens here. In addition to that, what happens once again, you have Y phase double switches, and this again you remember is the 0 crossing of Y phase. So, this is again another example of advanced bus clamping PWM. Here again you see the double switching phase, it switches around the 0 crossing. It double switches around the 0 crossing of the voltage, but now the phase clamping is different. So, the phase is clamped, every phase is clamped during the middle 30 degree duration. This is the middle 30 degree duration in every quarter cycle. So, this is 30 degree clamp, and that has been modified into an advanced bus clamping PWM. So, now this is advanced continual clamp PWM, this is continual clamp PWM, and there is some gamma can be anywhere between 0 and 60 degree, and instead of 7 to 1 I have written 7 to 1 2 here, instead of 0 1 2 I have written 0 1 to 1. So, I will use the sequences 7 2 1 2 2 1 2 7 etc. I will go on switching that like this, and here again I will do 0 1 2 1 0 1 2 1 1 2 1 0, I will go on switch like this. So, this is what I will do now. In this case, what will happen is once again a phase will be continuously clamped for a 60 degree duration, that is why we call it continual clamp, but a phase will also be double switching. Once again the double switching is around the 0 crossing here for 60 degrees centered around the 0 crossing, and that is the reason for calling it as advanced continual clamp PWM. And similarly, you have this advanced split clamp PWM. You have this advanced split clamp PWM. This is the same split clamp 0 1 2 I have replaced by 0 1 2 1, and I have replaced by 7 to 1 2. So, all that we are trying to do now is we had two possible sequences, that is 0 1 2 and 7 to 1. We constructed our bus clamping PWM using that. Now, what we have is we have two other sequences, what we call a 0 1 2 1 and 7 to 1 2. When I say a sequence, I include the reverse version of the sequence also, that is when I say I use sequence 0 1 2 1, 0 1 2 1 is used in one subcycle and 1 2 1 0 is used in the next subcycle. Similarly, 7 2 1 2 may be used in one subcycle and 2 1 2 7 will be used in the next subcycle. So, now with these two new sequences which I call as double switching clamping sequences, we can come up with these kind of advanced PWM methods, advanced bus clamping PWM methods. So, you had advanced continual clamp here and you have advanced split clamp PWM method here. These are not the only sequences, though I am not talking about the others right now. There are also two other sequences. What I can do is I can also apply a sequence called 1012, that is I am shifting this 1 earlier, I am just shifting this ahead, and I can apply this sequence like 2721, right. This is also possible. What I am doing here is in 1012 I am applying active state 1 for t1 by 2 seconds, and null vector for tz seconds, active state t1 for t1 by 2 seconds again, and active vector 2 for t2 seconds now. So, 1012 is also possible. The same way 2721 is also possible now. In this particular lecture on advanced bus clamping PWM method, I have chosen to restrict myself to these two. These two are the ones that were initially proposed and studied, and these two were proposed a little later, and they've been studied now. So, there are so you can just, all these are I would say as pretty recent, while something like 0121 was probably tried sometime back in a very different context, but it wasn't tried out in any big way. All these have gained kind of popularity, I would say, over the last decade or so. So, this is I have chosen to emphasize only this later, I mean in this module. When we do the later modules, when we are trying to analyze current ripple or torque ripple and so on, we would try to bring in the other sequences also and do this now. So, I am sure this would not have given, this would have given you some idea of what is advanced bus clamping PWM. Essentially we are relying on these kind of switching sequences, but it would not have given a very good feel for what it is. So, I am giving you two recent references in this topic. This is Narayanan, Krishnamurthy, Zhao and INR, advanced bus clamping PWM techniques based on space vector approach. This is published in Transactions on Power Electronics in July 2006. And I have another paper to tell you. This is T. Bhavsar and G. Narayanan. Again, this is in Transactions on Power Electronics. This is in October 2009. So, these two papers can give you further things on the two things that I told you here, this advanced continual clamp and advanced split clamp. Now, I am going to show a few more references now. So, these are the two references that I showed, and these are particularly about the advanced bus clamping which I discussed today, and this is about the double switching clamping sequence, trying to look at it from the triangle comparison side. Now, you see that here you can consider VRO average and this is MR star, this is VYO average and this is MY star. You can compare this with a triangular carrier, MR star with a triangle carrier, and produce the switching instant now, whereas for MY star you can't compare it with a triangular carrier. If at all you want to identify the switching instant, it has to be a very complicated signal as shown here now. This is not, this is a carrier, this is your usual carrier, whereas this is not your usual carrier. You are using a kind of an asymmetric double ramp signal instead of a single ramp here, and these slopes themselves will vary from one to the other now. So, triangle comparison is based on comparing a triangular carrier, and it presumes only one intersection with a phase in a subcycle, only one switching of a phase. Now, what we are doing is two switchings. Two switchings of a phase are not possible with triangle comparison method, it is possible only with space vector approach now. So, I am concluding a few things like this. Conventional and clamping sequences, many sequences are possible. These are possible using both the approaches, and division of null vector time is what is essentially done here. Whereas double switching clamping sequences cannot be implemented using triangle comparison approach. This involves division of active vector time, and active vector is applied more than twice. This is possible only using the space vector approach. Thus, space vector approach is more general than triangle comparison, because it can implement conventional clamping and also double switching clamping sequences, whereas in triangle comparison this is not possible, double switching clamping is not possible. So, you can read further about this in this particular reference on the two different approaches, right. And so, this is about the maximum DC bus utilization that you come to here, and by going by the peak value of this, I would discuss this later in the next lecture again. You would see that once again the peak phase fundamental is going to be 0.577 VDC, which is 15% higher than this VDC now. So, these are some of the references, I am just reproducing them. I had told you earlier about this. These are about space vector PWM, and this is a book on pulse width modulation, and these are about bus clamping and different kinds of methods. This is about bus clamping, how you can view it in the space vector and the triangle comparison methods, and this one is a tutorial paper. I have spoken to you about all of them earlier. I just try to recount here. Thank you very much. Thank you for being with me, and I will see you again in the next lecture. Thank you very much.